We go to example B. Example B. Find the vector functions, plural, functions, which yield the four face surfaces of the tetrahedron with these vertices. So you have a tetrahedron, you have four surfaces. I want to draw all of them. Yes?
Why would you take vector surfaces over the regular surfaces?
Over the regular ones?
Yeah.
Because these are truly functions, right? So you have an input. You never have a problem. You know, like on a sphere, you can't look at it as like a function of a single variable or even two, because you have a point up top and bottom. Like a single input gives you two outputs. That idea. With vectors, with vector functions, you don't run into that problem, because it's like the T used to be the clock in the background running. Now the U and V are like two clocks running. And so you can still have a function and never have to worry about any problems with it spitting out two different answers at the same time. That kind of makes sense? And then also, I'll show you, what we want to be able to do with this is find the area of a surface.
So
Arbitrary.
a circle has like a plus or minus value. This only has a single for each.
Yeah, I mean, if you take a sphere, right? And I say solve for z, you're going to have a plus or minus, right? Well, with this idea, you don't have that. So, we run into those issues in Cal 1 and in Cal 2 where it's like, well, let's just look at the top half, because you can't look at the bottom half at the same time. You have to do them separately. So this is just more powerful. Now, there will be, yeah, hang tight. You'll see. All right, you got this? You ready? Do y'all see the tetrahedron? It's got four pieces to it. All right, so let's focus on, let's see, we can pick any order here. Let's do that back one. You see the back one there? Okay, I'm kind of bring these out a little bit so they don't get in our way. Oh, you know what? My axes aren't colored. I need to go back and fix that. So this is X, this is Y, this is Z, right-hand rule. And when you look at that, I'm going to call this, let's call it R1 of UV, because it's the first of four that we're going to do. Okay, why don't I give you 30 seconds to see if you can come up with it. And then I'll take a volunteer. Is that a question, or you have it?
It's a question. So all these functions are going to be functions of the same U and V?
Yes, but they're different functions. So it's like T was before.
Still using just U and V.
Yeah, U and V for each of them, but they're in their own little universe, right? This one will draw that surface, and then another function we come up with will draw a
Okay, so
different.
the restrictions that we add are going to be separate for each function.
That's right. Each one of these is going to have a separate restriction and a separate component functions. Raise your hand if you have something. You want to go for it?
I just.
Or do you have a question?
Okay, so it's mainly a question.
Yeah.
So because we have the y constant, is that, or it's always zero? Can we?
Y is always zero.
Yeah, so we can hold that constant.
That's right.
Okay.
Well, just make it zero,
Hold-
right? On this blue little triangle, the y coordinate's always zero,
Yeah.
right? So at least that part's easy, right? We know that the y is always zero. Okay. We have control of two variables. So how do you want to control your x? Look at your x here. How do you want your x to vary? Go ahead.
I feel like there's like a cosine u from 0 to pi over 2, somewhere that's like.
You're bringing circles in.
Yeah.
Nothing is circular here. Go ahead.
Would you just set the x and z components equal to u and v, and because they're linear, so you would set the.
Okay. We have, yeah, okay, so let me try that. I'm going to put this down, and we're all going to work through this together, all right? Because I want everyone to see. All right, I'm okay with that so far. So what about u? How do you want to control the u? Between 0 and 3. Everyone okay with that? Our x, which we're calling u, right, has to go between 0 and 3. Now, we have to be careful here. Our v, which is our z, right, our up and down, our z, you cannot say that that z is between 0 and 2, because then that would draw a rectangle, wouldn't it? It would draw a rectangle. So you somehow have to control that z so that it draws this. Yes?
Can you use the slope, like setting the pole to each other?
Okay, so we need the slope of this line segment from here to here. Or we need to know, what is the equation of that line? Right? Do you know what it is? You have to be careful with what's positive and what's negative here. Time out. Aren't we going to need to find the slope of this line and like figure out what the equation is? And then we're going to have to do it when we do this one, and we're going to have to do it when we do this one, right?
Yeah.
We have to do it 3 different times. So the fact that I see that, I'm going to say, you know what, forget all that. I'm going to find the equation of the plane. That, you know, that plane that cuts through everything? This plane, right there, on that front side. Let's find the equation of that. And then I can use that equation to come up with all my lines. How do we find the equation of the plane that goes through these points?
The two dots and
Make vectors, cross them, right? We did all that back in chapter whatever. Yes? I'm not going to go through the work. I'm just going to tell you what it is, all right? Is that all right with y'all? Here's the equation of that plane. Y'all know what plane I'm talking about? That plane right there. The equation of that plane, after some work, is 4x plus 3y plus 6z equals 12. So I created 2 vectors, crossed them, that gave me a normal vector, then I used some point, came up with the equation, here it is. That's the equation of the plane. Now that's useful because if I'm back here looking at this, right, that one, and I wanted to know like what's the relationship that I have there? Remember what we said? Y was 0, wasn't it? And if y is 0 on this, this is kind of like work below this. If y is 0, then that tells me that the equation of that plane is 4x plus 6z equals 12, right? And I should solve this for what? Z. Why not x? What am I trying to restrict here? My z, right? I'm trying to restrict my z. So I'm going to solve this for z. And I get z equals, divide by 6, 2 minus 2/3 x. So that's the equation of, you probably could have gotten that already if you didn't do the plane thing. But now, see, this is going to work for any line we go across. All right, so back to this. We know that our y component's always 0. Our x is going to be between 0, our x component is going to be between 0 and 3, so we're controlling that with u. And then our v is up and down, but we need that v to be, what's the smallest we want v to be? 0, and we want it to go up to where? Never past that line, right? So 2 minus 2/3 u. Why u? 2 minus 2/3 u. Why u? Because what's x for us? U. X is u. Making sense or no?
Yeah.
Yeah? That's it.
Really simple equation for how weird it was to get.
Yeah. So look, in my code to draw this for you, probably hard to see from where you're sitting, but in my code to draw this, which one was that? The blue one? Where's the blue one? Oh, up here, very first one, blue one. I'm using something called parametric plot 3D as a built-in function, and I have u, 0, v. U is between 0 and 3, v is between 0 and negative 2/3 u plus 2. And it drew me that little piece. Yes?
Would there be a way to do it with a more complicated vector function but less complicated restrictions?
Perhaps,
Not reasonably,
yeah.
though?
No, I mean, there's nothing wrong with this. This is great. I mean, this is a very nice vector function, right? So keep it as is.
Yeah, I was just thinking if
There's more than one way you could draw that surface. There's more than one way. All right, you ready for that's 1 down, 3 to go. What's that? Yeah, okay, so now let's do that backside. Let's do that backside. All right, take a few seconds to try and come up with this one. I'll take a volunteer. Somebody, you can't go again if you've already gone. I really don't like investing all of this time, but we will spend as much time as we need to on this because like I said, I mean, you're going to need to be able to do this to move forward. I'll get back to you. Yes? Are you ready? Okay, you're ready. Okay, so go ahead. Tell me.
0.
0, that's because the red plane always lives in which plane? Okay, so the red triangle lives in the YZ plane, so the x coordinate's always 0. Go ahead. U.
And then 2 minus 2/3 v.
Where? Right here? Or
Yeah, where the v goes.
you want 2?
2 minus 2/3 u.
Okay, and what do you want u to go between?
Between 0 to 4.
Okay, good. I was hoping someone would do this. All right, let's see why this isn't going to work. All right, so look, here's the thing. How many variables are you using? You're only using 1, which means this draws a curve, not a surface. It's impossible to draw a surface without 2 variables. It's impossible. So what curve is this drawing? Let's see if we can figure out what it's drawing. So what you're doing here, you're saying that the x is 0, right? Okay, that's there. And now let's start with u being 0. If u is 0, you would have 0, 2, right? So that's the vector, that's this point right here, isn't it? And now let's let u be 4. If u is 4, you get 4 for the y, and then 4 here would give you, right? Something's off, right? Oh, you know what? Hold on. When we plugged in 0, we got 0, 0, 2. That's right. Hold on. We get 8/3. That, what should it be?
So that should be 0, yeah.
I want it to be 0, don't I? Did you solve this one? Did you solve it for x? Yeah, okay, all right. So but let's continue. Let's continue. Do you see that whatever you plug in for 4, you get another point, right? You get another point, wherever it is. And then as u varies between 0 and 4, what you're drawing is just that line segment, right? You're not shading the entire region. Got it? That's the most common mistake. So I'm glad that, I mean, this is why we're doing this interactive, because I want us to see the common mistakes. If you're ever asked to draw a surface and you only have 1 variable, it's not going to work, right? Okay. So can I ask you to think about it again? Like u is going to be the control on y, right? Do you want to go for it or no?
I'll let somebody else.
You sure? Go ahead, Greg. I'll be back. Yeah. So v here. What's my restriction on u?
0 to 4.
0 to 4. So that's going to control this, right? The u is controlling the y, 0 to 4. And I want my z to be here, right? Which is v, but I need to bound that, don't I? I need to bound that v. Go ahead, Greg.
Between 0 and 2.
2 minus 1/2 u. So where are you getting this from?
Just figured out the slope of the line and then started.
Did you use this or no? You didn't use this? I'm going to, but you're just using slope. That's fine. If I were doing this, what I would do is I'd say, okay, I'm on that plane. I'm trying to figure out where that plane hits right there. So that means your x is 0. And then if you solve this for z, and then divide through by 6. Z is always 2 minus 1/2 of the y-coordinate. And so if the y-coordinate's u, then you want your v to be bounded between 2 minus 1/2 u. Okay? All right, let's do the bottom one now. The bottom one, let's take that one out. So the bottom one, let's call that R3. Give you a moment to think about it. You ready? Go ahead.
So from the points, it's on the coordinates, right?
U comma v comma 0. All right. So what do you want what are your controls on u?
Controls on u were from 0 to 3.
0 to 3. So the u is the x component, so the x is going to go from 0 to 3. And then your y component, go ahead, v, is going to be
0 from negative 4 to 3 plus 4. I got that from the plane equation.
okay, so I'm going to provide 4 minus 3/4. 3/4, 4/3, 4/3 u. So again, that's using the plane equation over here. And we're saying, okay, this time the z is 0. And v controls the y. So I solve this for y. Solve that for y and divide through. We should get 4 minus 4/3 x, but x is u. So we replace the x with u, and we get that. This okay? You sure? No questions? Save the best for last. The actual tilted part of this thing. All right, so here's where things I think are really cool, all right? If we look at this picture from the top, there's no difference between that and what we just did, except for one thing, right? I mean, it's this shape that we just did. That was the one that was on the ground, right? That was the one that was on the ground. Okay, that one is the same as this one if you look at it from the top. So the big difference is that this z value, z coordinate, z component, is no longer 0. It fluctuates, doesn't it? And how does it fluctuate? Well, it has to live on this plane, doesn't it? 4x plus 3y plus 6z equals 12. It has to live on this plane. And so this z component is whatever z is here, right? So solve this for z. What do you get when you solve for z? 6z equals 12 minus 4x minus 3y. Divide both sides by 6. 2 minus 2/3 x minus 1/2 y, right? But for us, what's x? U, what's y for us? V. That's what my z component needs to be. It needs to be 12 minus 2, no, not 12, sorry, 2 minus 2/3 u minus 1/2 v.
Same bounds on u and v?
Same bounds, exactly same bounds, because what's happening here is that u is going between, u is the x component, it's going between 0 and 3. The v, which is the y component, is going between 0 and that line. And at all times, the z is bounded between, what, 0 and this plane right here, this plane equation. All right, let's check. I see you. Yeah, so you can see here, this is the actual instructions for the computer to do it. So I did u, I did v, and then I did 12 minus 4u minus 3v divided by 6. So I didn't reduce the fractions in when I typed it up. Okay, yes, question?
You could have used any of the other triangles to do that, right? Because if you look at it.
Yeah, you could have projected, like instead of this up, you could have done this one over, or that one over like that. They all look the same when you know, from the top it looks the same as the triangle on the bottom, but if you look at it from the side like this, it looks the same as that other triangle. Yep, so we could have done any of them. All right, let's go to the next one. We want to draw a cylinder. All right. Now this cylinder, what the heck? Yeah. This cylinder, yeah, it's hollow, okay? It has a radius of 1. I gave you the restrictions up there. It's not written on your page, right? On your handout, it's not written there. So please notice that the radius, x squared plus z squared equals 1, and then the y is between 1 and 4. Yes, Liz?
So we previously found the vector functions for each plane of the previous.
Yes. Uh-huh.
To make it like one big equation, we just.
You can't combine them together, no, because each one will draw a different surface. There's no way to combine them into one like master function that draws all of them together. So it's kind of like if I wanted to draw this, right? I would have to break this into like line segment, half circle. It would be 3 distinct functions, but now we're doing it in 3-dimensional space. All right. I'm letting you look and think. The red is the x, the green is the y, the blue is the z. Let's call this R, since there's only one thing to draw here. I'm looking for my next volunteer. Take your time. Have you gone? No?
No.
Okay.
So, rear,
Is this a question, or are you?
this is a
You going for it?
Going out and answer, yeah.
Okay.
And I'm very prepared for this to be wrong, but would it be cosine u, v sine u?
Cosine u,
Yeah.
v, sine u. What are your restrictions?
It'd be 0 to 2 pi on the u, and then 1 to 4 on the v, right?
What do y'all think?
What's the radius?
The radius is 1. The radius is 1.
Hollow, so we don't need to have the fluctuation.
You don't have fluctuation. What do y'all think? Agree, disagree? Let's, pardon?
I'm saying x and z.
Yeah, so what does this do? This right here draws me a circle in the xz plane with a radius of 1, right? That means, like, if you were to look at it from here, that's supposed to be a circle, not a disky looking washer, right? That's just a circle. How do we draw a circle of radius 1? Cosine u sine u, right? And we're using the x in the z because it's in the xz plane. The only thing we need now is just to bring that thing backward and forward, right? So we control that backward and forward down the y-axis with v. And we just let that vary between 1 and 4, and that will move. It's just basically drawing a bunch of circles, right? It's drawing a circle. That's with the v being 4, right? And then the circle in the back is with v being 1. And then everything between draws you all these circles like that, and you draw eventually the whole cylinder. So there's no need to control this number in front of the cosine and the sine because it's a fixed radius the whole time, right? That's different than the disk. To draw a disk, you need the cosine u sine u, but you need the v in front to get the whole disk, right? So you use up 2 of your variables when you're drawing disks. But to draw the cylinder, you need 2 variables as well because you need to control that middle v. Questions there? Yes?
You want a cylinder solid
Yeah.
And you already have a restriction on it.
So yeah, so it's a good question. If we wanted to have this be solid, could we do it?
Would you have to solve for the restriction on V because you would need it?
If we do a vector function of one variable, we can draw what? A curve in three-dimensional space. If we have a vector function of two variables, we can draw a surface. What do you think it would take to draw a solid in three-dimensional? We would need three variables. So what you could do, imagine we were allowed to have a third variable, which we're not. This book doesn't talk about it, but if we did, then what if we had a new variable? Call this W next to it, right? And just put a W here and a W there and let W go between 0 and 1. Voila, you have a solid bar now, right? Because the W now controls your radius. So you got, this is taken care of. This is drawing a disk, right? That's drawing a disk with the radius between 0 and 1. And then the V is just taking it back. So you get the solid. So you need a third variable, unfortunately.
Need to use W4B as well?
Pardon?
Do you need to use W4B scale?
A W for V?
Yes, sir.
No, because all the V is doing is moving it backward and forward. That right there draws disks, right? That draws disks. Radius, 0 to 1. And then this just moves it back and forth. All those disks. Does that answer your question? Yep. Okay. So interesting now. What if you have a vector function with 4 variables in three-dimensional space? What does that draw? Okay. Yeah, so now you start having more variables than the dimension of your space, right? And that could be an issue. Let's go to the next example. So for this one, it's the same cylinder we were just looking at, the same one. Okay? But all I want this time is the red end cap. Where is it? All I want is that red end cap. I'll take a volunteer when you're ready. Just the red end cap. It's the same exact cylinder we had just a moment ago, but I don't want the actual cylinder, I just want that red end cap. You want to go for it?
It would be the same, so I think instead of V, you would just have 4.
Let's see. Yeah, so when you say same, what do you mean?
Cosine U,
Cosine U,
4,
4,
and
sine U, close. So this is just going to draw you the circle of radius 1, right? You need the whole disk. See, notice again, you're only using 2 variables, right? So this is, yep. So we'll put a V in front, V in front. Let me give myself a little more room. So V cosine U, 4 V sine U. And here your U will go between 0 and 2 pi. And your V, you want to draw a unit disk, right? So the radius was 1, so 0 to 1. On all these problems, just remember, you should always be using both variables or else you're going to be drawing curves. I remember when I was learning, I was like, that was the one thing I would put it together, I'd be like, wait a minute, I'm only using one variable. This is not drawing a surface. And I have to go back and rethink, what am I missing here? All right. So for this one, I need to give you some information that's not on your sheet. The information that I need to give you is that this blue cylinder has as its equation x squared plus z squared equals 1. I need to also tell you that this right here, that piece that's slicing through, that's a plane, right? That is a plane that's slicing through. I'm going to give you the equation of that plane. That plane has the equation x plus y minus z equals 2. And then finally, on the back side of this, right, the back side of this thing is y equals 0. Go ahead and just jot those down. That would be given to you, all right? Without giving that to you, it would be impossible to do this. So let me spin this around for you. We have the back side of this, right, which is a disk. We have the front side of this, which is a disk, but it's like tilted, right? So it's not truly a disk. And then we have the cylinder. Let's start with the easiest one. Which is the easiest one? That back one right here, that disc in the back?
Can you move it around to see what it looks like?
Yeah? All right, so let's start with this one in the back. The one in the back there, let's call that one R1. It's a disk, right? We just did a disk. So we need, who's up? Need a new volunteer.
I know how to do this one now.
Let's see if anyone else. You ready? Go ahead.
It's just b cosine u 0, b sin u
Yep. U between
0 and 2 pi,
0, 2 pi,
0,
0 and 1. Y'all got that? We have the 0 for the y because it's sitting right. It's sitting there on the xz plane. That's why we have a 0 as the middle component. You got disks down, right? Kind of. All right. So let's go after the next one that I think is more natural to go after, and that's this one right here, which is almost the same thing we just drew, isn't it? Like if you look at it, from the back, you've got that disk, right? And if you look at it from the front side like this, it's that same disk, except that it's like coming out at you and it's tilted, right? So to draw this, I need R2 of V. Who wants it? Who wants it? Who wants it? Who wants it? Do you have to draw the same disk in terms of the xz? Is your xz going to be the same? Yes? Right? Look at this disk. This right here is the same disk with respect to the xz plane. Right? With respect to xz, it's still a disk. The only thing that's different is the y, right? The y kind of like goes away from you and comes out at you.